Okay, more information on IVT. So IVT says if we have a continuous function and we have some value between f of a and f of b, like k, then there has to be some x value that gets there. That's all it really says. Extreme value theorem says that if it's a closed interval, there is both a minimum and a maximum on that interval. Now, it could occur at several places. It could occur at your endpoints or your critical values. So you have to check all of them. Mean value theorem says that if you find the slope between the two endpoints, if this is a continuous and differentiable function, then there will be some place where the instantaneous slope, tangent slope, is going to be exactly the same. That's really all it says. So let's kind of go through some examples, and I definitely want to go through these with you because the copy didn't come out very good. So I believe that says 1, 3, 6, 9, and 10. Okay, so we have a differentiable, and we want to find the average rate of change on the interval. Average rate of change just means we're going to take f of 10 minus f of 1 divided by 10 minus 1. Change in y over change in x. So f of 10 is 3. F of 1 is 0. Divided by 10 minus 1, which is 9, gets me 1/3. So, there exists some value c in that interval such that its derivative is also 1/3. Because f is y. So if we're talking about that there is a derivative, then the function has to be differentiable, and it is. On the interval, and we're talking about it's differentiable on that closed interval, since it is given that f is differentiable, by the mean value theorem. There exists a c value in 1 to 10 where f of c is 2. Doesn't show it in the table, but how could we prove it? Well, because f is continuous on the interval 1 to 10, and we know it's continuous because it's differentiable, and let's look. What's the smallest? So f of 1, which is 0, is smaller than 2, and f of 10, which was 3. That means there has to be some y value of 2 by the intermediate value theorem. F attains both a global maximum and a global minimum on that interval because f is continuous on the interval 1 to 10, since we're given that it's differentiable. And if we're talking about global maximums and minimums, those are considered extremes. All right, so let's see what else we got. F of 3 equals f of 10. So we back at the table. F of 3 is 3. F of 10 is 3. It does. Since that's true, then there exists a C value in that interval such that f prime of C equals what? Ooh, let's see. So if f of 3 and f of 10 are the same, then if I found the slope between them, what would that slope be? It would be 0. So f prime of some value, C, is going to be 0. Because we're talking about a derivative, so we're talking about differentiable on the interval from 3 to 10, including 3 and 10, true, since it is given that it is differentiable. And which theorem says that there's going to be a derivative that equals the same as the slope between 2 points? That's mean value theorem. Ooh. F double prime is going to be less than 0 on 3 to 10. What must be true at the C value from problem 5? So if we know that the second derivative is less than 0, and we know that f prime of that value is 0, what must be true about C? Okay, that's concave down. So that means we have C is a maximum. Find the smallest interval on which it is certain that f of C equals 2. Smallest interval. So we're looking for y values that have 2 in between them. Well, here we could have a 2 in between them. That's between x is 1 and x is 3. That's actually the smallest, from 1 to 3. Find the smallest interval on which it is certain that there's a derivative that equals -1. Ooh, so we're going to have to do some playing here. So I'm going to look back at my table and look at some derivatives. Change in y is 3, change in x is 2. That doesn't work. Change is 4, change is 3. Doesn't work. Change is down 2, up 3. Down 2, up 1. Oh, there it is. Nope. That doesn't do it either. So now I've got, okay. From here to here is 7 and 5. Nope. I need to get negative, right? So let's ignore all of that. From here all the way to here, it's going down 4, up 4. Down 4, over 4. That would do it. So between 6 and 10. Next one. True or false? Ooh. 0 is less than or equal to f of x is less than or equal to 7 on 1 through 10 by EVT. Do we know that every f of x value is between 0 and 7? No. I don't know if 7's the maximum. False. Could there be a C value between 6 and 9 where I have another y value of 8? Well, 6 is 7. Oh, and 9 is 5. So f of 6 is 7. f of 9 is 5. Oops, sorry. And 8 is not between those. Since 8 is not between them. Then IVT doesn't work. Sketch an example of a function which is defined at every value x on a closed interval, but which does not have an absolute maximum. Now notice it says it's defined at every value x. Does it say it's continuous? No. Oh, this is interesting. So an absolute maximum. I'm going to let y'all play with that one. Because there's so many different ways you could draw it. But the thing is, if it's to be a violation of EVT, though EVT, you had to be continuous. And this doesn't say it's continuous. Find the average rate of change of g of x equals the absolute value of x on the interval of -1 to 3. Well, that would be g of 3 minus g of -1 over 3 minus -1. G of 3 is 3, g of -1 is 1, and that's 4, so that's 2 over 4. Explain why MVT does not guarantee a C value that has that same slope. Well, MVT does not apply because g of x is not differentiable at one certain point. Which point is that? At x equals 0. It's a sharp turn. H of 2 is -3, h of 5 is 3, and h is defined at every x value on the interval from 2 to 5. Sketch a graph on which h has no x-intercept in that interval. Okay, and it says define, but it does not say it's continuous. H has to be continuous for IVT to work. I mean, this one's kind of easy to do if you, so you have 1, 2, 3, 4, 5. There's my x values. Okay, so I have -3 would be here, and this would be +3. If everything's defined, but we don't have any x-intercepts, that means maybe we go to here, and then it starts back up here. It's defined for every x value, but it's not continuous.